Okay, so this is number 4D, partial fractions. Integral of 10 divided by x minus 1, x squared plus 9 dx. So the trick on this one is to figure out how to set up your partial fractions. Remember that you first want the denominator factored completely. I can't factor x squared plus 9 any further, so that is factored completely.
You have to determine whether it's
In general, you do. This one, because there's no x's on top, it's proper. The degree on bottom is higher than the degree on top. So we do not have to do the long division step like we did on letter B. But what we are going to do is we're going to write a fraction with each one of these in the denominator. Right? And we want to figure out what goes up here in the numerator so that this splits into these two. And so
A and B.
we put unknowns up there. If you put 5 and 5, it doesn't work, right? Because the only way you can add fractions is if they have a common denominator, right? So putting a 5 here and a 5 here, when you add them up, before you add them, you'd have to multiply by the missing terms from the denominator to make a common denominator, and that won't get you to 10. So we put unknowns up here. We put an A on top of this one, but you don't just put a B here because it's quadratic. It's a bx plus c. You do 1 degree less than the denominator. That was like our second or third case. Okay, so now I've got to find A, B, and C.
So now can we factor out x squared plus 9?
Well, what I do is I get rid of the fractions entirely, multiply it completely through by x minus 1, x squared plus 9. Multiply everything times that. Multiply both sides of the equation by the common denominator. And on the right-hand side, it means distribute it to everything on the right-hand side. What happens on the left is everything cancels, right? And I did just 10. On the right-hand side, on the first term, the x minus 1's cancel, so I have a times x squared plus 9. And on the second one, I have bx plus c times x minus 1. Usually the easiest way to do this is to just guess good numbers, which I can still guess one good number. If I choose x equals 1, it cancels out this whole term over here. And all I've got left is an a. I've got a 1 plugged in here, so I have 10 equals 10a. So if I let x equal 1, that means 10 equals a times 1 squared plus 9 plus a whole 0 over there. Because when I plug in a 1 right there, that goes to 0. So actually what I have here is 10 equals 10a. So what is a? 1. But there's not a good x to plug into this one.
I was going to say -3,
But -3 doesn't work because the square cancels, right? So you have two choices. One, you can just try any other two numbers that you want. You're going to get 2 unknowns. Or you can do my other technique where you collect them all together. I say let's just choose other values. Let's x equal 0. Just picking a simple one to evaluate. 10 would then be equal to, I know a, by the way, is now 1, so I'm going to go ahead and plug that in. 1 times 0 squared plus 9 plus, now b times 0 plus c times 0 minus 1. So this is 10 equals, that's 0 squared plus 9, so 9 times 1, 9, plus, that's gone. And c times a minus 1 is minus c, right? That's gone, c, 0, 1. So just minus 1 times c, minus c. Okay, so 1 equals minus c. C is then negative 1.
Why'd you go to 0 for bx plus c on the first one? X equals 1.
I'll put a 0 here.
No. When we simplified it, we added 1 to the equation. When you said like x equals 1.
1 minus 1 is 0 times.
Why did this become 0 here?
Yeah.
Because when I plug in a 1 here, I get b times 1 plus c all times 0. Right? 1 minus 1. That's 1. Sure. Good question. All right, so let x equal something else. I don't care what. Pick a number. It's not 1 and 0. 4? Oh, okay. Why not? I mean, I'm going to have to square it. It's going to be big, but hey, that's fine. I might do negative 1. I might do 2, but I'm going to do 4 because you guys said 4. 1 times 16 plus 9, right? 4 squared plus 9 plus b, I don't know, but x I'm letting be 4. Minus 1, right? Just plus a c, so minus 1, and then 4 minus 1. All right, so 10 is equal to 25 plus, this is 4b minus 1 times 3. So 10 equals 25 plus 12 minus 3. So 10 equals 25 minus 3 is 22 plus 12b. So minus 22 minus 22 is minus 12 equals 12. B. So B is negative 1. Okay, so since it's up above the screen, let me just rewrite what I've got. I've got that 10 over x minus 1, x squared plus 9 is the same thing as 1 over x minus 1 plus a negative x minus 1 over x squared plus 9.
How did you know to choose 4 though?
Oh, I didn't. You told me to choose 4.
So you just guessed?
It doesn't matter.
Guess it.
As long as you choose another number. Now, usually what happens, I'm gonna jump out of this for just a second. If I go back to the day that we did that, on 7.4.
So any number will work.
Right. A lot of times, you end up with an equation that looks like this one right here. It's got some highlights on it, but try to look at the structure. You had something on the left-hand side equals a times 2x minus 1 times x plus 2, a b times x plus 2, a c times x times 2x minus 1. I look at that and say, what are some good choices for plugging into that? And it's anything that makes one of those x terms 0. So like choosing x equals 0 is good because it knocks this one out and it knocks this one out. Choosing x equals negative 2 is also good on this one because it knocks this one out and it knocks this one out. Choosing x equals 1/2 was good for this one. So usually you can tell by looking at whatever makes one of those factors on the right 0. The problem that we had on the one we were working on is that nothing makes x squared plus 9 0. Nothing does. So I just chose arbitrarily some other numbers. 0 was a good choice because it knocked out this guy. I could have chosen 2, I could have chosen -1, just anything to plug in so that the only unknown left in my problem is b. So don't get hung up on why I chose 4, I just chose a number that wasn't 0 or 1. But do you see how up here I had 10 x minus 1 x squared plus 9 equals whatever a is over x minus 1. So that's why 1 over x minus 1. And then I had plus bx plus c over x squared plus 9. Now b is -1, so negative x plus c, c is minus 1, so minus 1. Now, if you went back to your college algebra days and were asked to, or your high school algebra days, asked to combine these two together and simplify, you find a common denominator, multiply the missing denominators, multiply out the numerators, collect like terms, guess what you'd get? This thing, right here. But the thing on the right is easier to integrate. In fact, it's one step further to integrate. Generally, when you have an x squared like this, you split this up into 2. So I take one more step and do 1 over x minus 1 minus x over x squared plus 9 minus 1 over x squared plus 9. Just split up the numerator. Now you've got 3 fairly easy integrals. This one, and this one. So I have integral 1 over x minus 1 dx minus the integral of x over x squared plus 9 dx minus the integral of 1 over x squared plus 9 dx. Integrating each of these now separately. So that's log of x minus 1. This one I would do with substitution. X squared plus 9 du is 2x dx. So put in a 2, take out a 1/2. There's your du. There's your u. This becomes the integral of 1 over u. Which is the natural log of u, and u is x squared plus 9. Did a few steps in one right there, but that's just using substitution to integrate that. Hopefully by now it's not completely foreign to you. And the last one, 1 over x squared plus 9. I gave you a formula for these, but whenever you have the integral of 1 over x squared plus a squared, that's, I think, where is it? Actually, it's on your formula table, but I gave it to you in class. I think it's 1 over a tangent inverse of x over a. Where is it? Oh, it's number 17, yeah. So 1 over a tangent inverse of x over a. So this becomes 1/3 tangent inverse of x over 3, all plus c. So that's the hard one, the longest one of number 4 for sure.